Let's discuss question number 29 from test 5. This is from heat transfer. A thin tube heat exchanger is used to heat. So you have a heat exchanger which is used to heat air. Air volume flow rate is given 2.36 meter cube per second and enters at 1 atmosphere 15.55 degrees Celsius and comes out at 29.44 degrees Celsius. Hot water enters at, so you have a thin tube exchanger. I am just drawing one of the tube, and you have the water here and you have the air here. Water is hot, okay, and it enters, hot water enters at 82.22 and then flows across the tubes, producing overall heat transfer coefficient U, which is 227 watt per meter square degree Celsius, and the total surface area is given as 9.29 meter square. So this is a tube exchanger, parallel tube you can say. Calculate the heat transfer rate. Well, heat transfer rate, how much has taken from air to water, or sorry, water is hot, so from water to air. So now we know the temperature of the air, we know the temperature of the inlet and outlet of the air. So obviously the heat that has transferred from air is mass flow rate into specific heat of the air into it got heated up. So T outer minus T inner for the air. So if we do this for the air, that is the heat that has come from the water, right? So that will be the heat transfer rate. But specific heat for the air, we know it is 1.007, 1.005 the specific heat for the air. So only thing that is left, temperatures are given, so only thing that is left is calculation of mass flow rate. Okay, 1.005 or 0. So this also we know, temperatures are no, only thing is mass flow rate. Well, we know the volume flow rate at the start. So if I can find out the density into the volume flow rate, that is nothing but the mass flow rate, right? The volume flow rate is given. So density, how do I get? If I assume it's ideal gas, so PV is mRT, m by v is density. So this is pressure, this is density. I'm writing rho by RT, so rho will be P by RT. So let's find out the density first and then we'll just multiply. So the pressure will take the 1 atmosphere, that is 1.0132 into 10 power 5, and R is your 287 for air, and the temperature as the starting temperature 15.55 plus 273. So if I calculate this value comes out to be 1.223 kg per meter cube. Okay, because this is 287 is joules, it's not kilojoules. Okay, it's joules per the required unit. Okay, joules per your degrees kg Kelvin. Okay, so this is the density, and this density if I use it here, so 1.223 into the volume flow rate 2.36 meter cube per second. So this value comes out to be 2.9 kg per second is the mass flow rate of air. Once I get the mass flow rate, I'll just use this. I mean, all this is redundant data about the overall heat transfer and A, because the temperature of other things I don't know, and again you have to use LMTD method and other stuff. But then I know for one of the fluid both the inlet and outlet temperature specific heat. Only thing is mass flow rate calculation, which we have done. So 2.9 into specific heat 1.005, outer temperature 19.44 minus inner temperature 15.55 at the inlet. So this is the mass flow rate. This comes out to be 40.5 because of this kilojoules per second is 40.5 kilowatts. So the answer for this is C, 40.5 kilowatt.